pure. Vabbè, aspettiamo un minuto e poi... Cominciamo così sì, okay. So, guys, I think we can start. Welcome to the Geography Lab. And today we have 3 speakers, so we will straight start with the first one. It's Piero. He will talk us about Eureka Progress Surveys, multi-resolution also. Go ahead with your...
Good afternoon, everyone. This is the paper I want to present you today. Hierarchical progressive surveys, multi-resolution LPX data structures for astronomical images, catalogs, and 3-dimensional data cubes. Modern astronomical projects have been producing normal source catalogs, which may contain up to 10 to the power of 12 entries. Just think about Gaia and LSST projects. Just think about Gaia LSST projects. Nowadays, several large surveys are available through astronomical data centers and services. And these interfaces usually provide a query form which allows us to cut out regions of the data. However, for large area studies, this approach is not practical because downloading the data for large regions at the original fixed resolution is not efficient. And so it is difficult to use a survey as a whole, and even more to combine and compare multiple surveys. However, on the other hand, there are many visualization tools able to display interactively multiple surveys across the entire sky. These interfaces use hierarchical techniques to enable fast multi-resolution visualization. One of the most famous interfaces is Aladdin. Aladdin employs a hierarchical multi-resolution tessellation of the sky called LPX. LPX stands for Hierarchical Equal Area Isolatitude Pixelization. And today I wanted to present you the Hierarchical Progressive Survey System, which is based on LPX and that has been developed to support the visualization of astronomical data such as images, catalogs, and 3D data cubes into Aladdin. So let's start with LPX. LPX is a curvilinear partitioning of the sphere with a tree structure that supports multi-resolution applications. As you can see in that picture, LPX uses a base resolution that divides the sphere into 12 pixels. And these pixels are recursively divided into 4 subpixels in a 2x2 pattern to create finer and finer eigenorder meshes. A mesh with a given order k has a resolution defined by a number, n-side. N-side is simply the number of divisions of the original base resolution pixels. And the relation between the order k and n-side is simply n-side is equal to 2 to the power of k. So a mesh with a given n-side has 12 times n-side square pixels, and the pixels with the same order have equal area and are arranged in rings of equal latitude. Okay. The IPS system organizes astronomical data into LPX maps of different orders and so different resolutions. For the sake of definiteness, let us think about an image. Firstly, we resample the image onto a set of LPX maps of increasing order. Okay. Since it would be impractical to access and transfer individual LPX pixels, IPS groups the pixels into tiles as the basic unit of a new map that is transferred when any of its pixels are needed. So the IPS structure is defined by a set of LPX maps of order k, n-tiling n-tile, where n-tile square is the number of pixels inside each tile. For example, if these little ones are the original pixels, then the bigger ones are possible tiles with n-tile equal to 1, 2, 3, 4. Okay. The tiles define also the basic unit of storage. In fact, each tile is encoded as a square array into a file, and all tiles of the same order are included into the same directory. So the structure is very simple. Okay. The most direct use of IPS is the mapping of an astronomical image into IPS tiles. The IPS representation of image survey is generally constructed by resampling the images onto a LPX map at the maximum desired order Kmax. Then the tile images for all the tile orders are generated. The flux at order k is conserved by simply averaging each set of subpixels at order k minus 1. Okay, we should, when we construct the IPS image, we should keep attention to the choice of the maximum order, which should be close to the original angular resolution. Moreover, the minimum order tile order to be included should not be too low. In fact, tiles with order equal to 0, 1, or 2 are too large. They have size lengths of 10 degrees or more. So usually IPS images have tiles with order greater or equal than 3. Here it is reported as an example the IPS representation of the GRIMPS survey. As you can see, the IPS scheme is general enough to handle data with any kind of sky coverage. And this representation has been generated with the CDS HGen program, which is freely available. IPS enables also the manipulation representation of source catalogs. A IPS made of multiple tiles with different orders can provide different views of the catalog as a function of the resolution. Ok, quindi the tiles are filled according to a sorting key. The sorting key can be defined by any quantitative property. So the sorting key determines the distribution of the sources inside each tile order. A sequential view of the tiles would show the distribution of the sources inside each order, as you can see in the upper panel. But more commonly, a cumulative view is adopted. IPS catalogs can be generated with the CDS IPSGenCat program, which is also available. For what concerns IPS cubes, the basic idea is very simple. We split the cube into planes along the 4 dimensions, which can be the time, the frequency, etc. And we generate a IPS for each plane. Each plane is an image. Okay, so at the end, each tile will have multiple frames, as many as the number of planes. Okay, so you can construct your own IPS images, catalogs, etc. with the programs I said before, and then put them into Aladdin and take advantage of all Aladdin features. Here there are some examples for some galaxies images, but I remember you that Aladdin can easily manage and manipulate surveys across the entire sky. So let's come to the conclusion. Hierarchical systems describe the data in a multi-resolution manner that facilitates efficient access to the data and conserves their scientific properties. Hierarchical systems scale easily so that they may handle larger small data sets in the same framework. The use of a generic hierarchical system for the wide variety of astronomy data enables new levels of interoperability. And finally, IPS makes scientific use of astronomical data easier because it uses a sky tessellation that was directly translatable into astronomical coordinates. It supports accurate photometric properties of images that would allow scientific computation directly on the hierarchical grid pixels. It provides a way to link directly to the original progenitor pixels or catalog data, and the use of a simple file system structure to organize the tiles of a IPS makes it very easy to publish IPS to the web. Yes, thank you.
Any questions?
Yes, I think.
Yeah, that's why you read it.
Yes.
Other questions? Okay, so thank you again. We can move to the second speaker. So we have Giuliano Antonincello with polarized scattering and geosignatures in exoplanetary atmospheres.
Sì, non basta prendere cos'è? Okay, so this work aims to study the feasibility of detecting biosignatures in exoplanetary atmospheres using spectropolarimetric technique. So, the first problem is setting a correct radiative transfer equation for the atmosphere of the exoplanets, including all the effects due to different polarization modes. The author considered an intensity vector composed of 4 components, which are the total intensity and the 3 Stokes parameters that give the intensity of the different polarization modes. Once the problem with this equation is settled, we have to choose a so-called source function that takes into account both the thermal emission of the planet and the atmosphere, and also the scattering source function, which is a function that takes into account also the scattered photons inside the layers of the atmosphere and the scattered photons by the planetary surface in case the surface has a higher reflectivity. So the problem is really complex, and the author developed a model to build a proper source function for this problem. Because it depends on the chemical composition of the atmosphere, the physical state of the atmosphere. So clouds strongly affect the final results of its simulation, and of course the thermal profile of the atmosphere, since this affects strongly the black body term in the source function. The general solution of the problem cannot be written with an analytical function, so it's not an analytical solution. And all this work is based on simulations conducted essentially on integrating this function over different chemical composition and geometrical properties of the planetary surface and the planetary atmosphere. A fundamental parameter in this model is the total optical depth of the atmosphere, because essentially this parameter determines how much energy is coming out from the planetary atmosphere. So, a first important phenomenon involving both scattering and polarization is, of course, Rayleigh scattering, which is an optical phenomenon that occurs when the wavelength is greater than the particle size, and it is a commonly seen phenomenon, since our blue skies are due, in fact, to Rayleigh scattering of solar radiance in the Earth's atmosphere. And this is something that happens also in, we would say, something more strange. For example, in hot Jupiter's atmospheres, like this example. This is a simulation conducted in a planet with an effective temperature of 1,500 Kelvin, which is something like the typical scenario of the hot Jupiter planet. And we see here three different simulations for three different values of the semi-major axis. So these simulations are strongly dependent on the fitted results for the radial velocity model that gives the planetary mass, but also the orbital parameters. And we see here plotted the total radiation, which is the dotted red line, and the contribution due to different phenomena, optical phenomena in the atmosphere. We have the thermal radiation, which of course increases when the optical depth of the atmosphere increases, the single scatter radiation from the hot star, and the multiple scatter radiation from the hot star, and also the planetary atmosphere. This single and multiple scatter radiation affects the total polarization degree of the outcoming radiation from the planetary atmosphere. And in particular, the single scatter radiation from the photons of the hot star is the principal responsible of the polarization of the outcoming planetary irradiation. We see in the lower panels also the situation at the upper boundary of the atmosphere, so where the optical depth of the atmosphere is 0. And we see here in red the linear polarization coefficients and the total intensity in black. Here, of course, the model does not take into account all the chemical species that may be present in a planetary atmosphere. So the opacity sources are only a few molecules and atoms that are likely to be present in the hot Jupiter's atmosphere. So what we see here is that polarization is stronger at 90 degrees, of course, because the Rayleigh scattering has an intrinsic property that makes the scattered radiation, which is polarized, stronger at 90 degrees from the direction of the incoming radiation. And so the author concluded that polarization is due, of course, to the anisotropy of the incoming radiation and can grow up to 100% at 90 degrees. And of course, it's suppressed where the thermal radiation dominates, for the reason that in the source function we have seen in the first slide, the thermal source term dominates over the other terms. Then anisotropy is highly sensitive to the incoming external radiation because, of course, maybe this is quite we will say something obvious, but the Rayleigh window, which is the blue region of the spectrum, is also the region in which the stellar radiation is more anisotropic. So this phenomenon is particularly important also because the source of radiation perfectly matches the region of the spectrum in which Rayleigh scattering is more effective. Then single scattering contribution to polarization increases with the stellar flux, and so this is particularly important in the case of Jupiter, so large planets very close to their host star. And polarization, of course, is highly sensitive to the host star variability because of what we said so far. If we have spots on the stars that have rotational modulation, and so a rotational modulation of the incoming flux at the upper layers of the planetary atmospheres, we have also a rotational, modulation with the same period of the stellar rotation, also on the polarization signature of the planetary atmosphere. Another optical phenomenon is the mean scattering, which is something that occurs when the wavelength of the incoming radiation is comparable with the particle size. And it is quite interesting. Here we see some results of the simulations where supposing a gamma-like distribution for the particle size, which is something that is physically plausible because many thermodynamic arguments can be used to in favor of this kind of distribution of the particle size. And we see that forward, this is the angle of scattering, so forward scattering dominates for larger particles, which are on the left of these panels. Well, a strong polarization here, and we see in the second panel, appear in the region of the so-called primary rainbow. This is the same phenomenon we see when we observe a rainbow in a rainy day. And this is due to the mean scattering. And of course, this could happen also on exoplanetary atmospheres. And although the author says that this is a very interesting phenomenon, he poses some strong arguments against the feasibility of observing such a phenomenon because it's very faint, especially compared to the polarimetric signature of the Rayleigh scattering. And of course, as particle size increases, then the results became more similar to the geometrical optic results. And so weak polarization is observed as small scattering angles. Another probe of the chemical composition of the exoplanetary atmosphere is observing the molecular bands, because these molecular bands show weak correlation between their total absorption and their polarization degree. So we could use polarization as a proxy for the absorption lines in planetary spectra of molecules, and this means that we could use spectropolarimetry as a proxy for the chemical composition of the planetary atmospheres. So the most interesting results is that all combined, these tools can give us hints of the presence of the so-called biosignatures in exoplanetary atmospheres, which the author considers something like chlorophyll, or as in literature they are called biopigments, which are composition of different kinds of chlorophyll and other molecules, complex molecules present especially in cyanobacteria. We see on the left that some plant samples, earth plant samples, spectra show a polarization that is stronger at wavelengths where the absorption is greater, and on the right the consequence coming out from the simulations of an observation of spectra of Earth-like planets with an 80% of land cover with biopigments, that is plants, and 20% of land cover of ocean. Of course, we see this anomaly, the black line, which is what we will see observing the spectropolarimetric data of an ocean planet, and we see a strong degree of polarization, and it's because oceans are a smooth surface, and so the reflected light from the stellar irradiation will be almost totally polarized. So the most favorable scenario to observe and detect biosignature in an exoplanet is, of course, an ocean planet with an optically thin atmosphere. It is one of the most important results of these simulations. So, conclusions. Detecting life on exoplanetary atmospheres is maybe feasible. The major problem in detecting surface features which are hints of the presence of biosignatures is that we cannot resolve exoplanetary surfaces, but surface features can be detected from rotational modulation of spectropolarimetric data for the reason we have seen. So this is not an easy task because especially in optically thick atmosphere this is not feasible at all, because clouds can mask all the signatures of biopigments and also of any other source of polarized light, and in fact they are the most disturbing factor in detecting biosignatures. All this considered, the author concludes that spectropolarimetric, especially with the incoming instruments at the ELT, is the most promising tools if we want to detect signs of life that are non-equilibrium processes that produce polarized radiation in exoplanetary atmospheres. And this will be a major theme for research in the following years. Thank you.
I don't understand why we should see polarized light formed by pigments. I mean, maybe they are in leaves or in different stuff.
Because the scattering of light on biopigments produce strongly polarized radiation.
But I guess if I choose leaves, they will produce a different polarization. Right?
Yes, but if you observe a spectropolarimetric data set which exhibits the features of the one we see here on the left, we can conclude that it's probable that probably on the surface of this planet, if it's proved it has an optically thin atmosphere, there is something like chlorophyll producing polarized scattered radiation.
You mean like a lake of chlorophyll?
Maybe a
the
lake
chlorophyll
of...
is inside leaves and the leaves are...
No, because cyanobacteria and algae can be found also in lakes, oceans, so we don't know what kind of organisms may be present if they are on this planet. But if they are photosynthetic organisms, they are likely to produce biosignature in spectropolarimetric data that resemble the ones we have seen here.
So we have time for another question.
You cannot apply this technique for Venus, for instance, but for Mars, for Venus.
No.
For Mars, you can.
For Mars we can, but I think
Do you know if
it's cheaper going directly on Mars and
yeah.
digging a hole.
There's been applied to Mars,
Yes.
and they found nothing.
They found nothing.
I don't know. I mean, I'm asking.
the hypothesis is that if there's some non-equilibrium process as a proxy of life, of course, in the Martian environment, it will be well beneath the planetary surface.
Okay, so let's thank you again. We are running out of time. Okay, so let's proceed with the last speaker of today. That is Dara, and she will talk about the interaction of the halo around the butterfly planetary nebula NGC 5 blah blah with the interstellar medium.
Okay, thank you. Let's start from the object of this paper, which is NGC 651. It is a well-known planetary nebula, known since the end of the 18th century. It is a typical example of a bipolar planetary nebula with butterfly morphology, composed by a thick equatorial waist seen almost head-on, and two broad bipolar lobes which are really extended. The subject of this analysis is the interaction between the planetary nebula and the surrounding interstellar medium. Observation of planetary nebulas show different stages of interaction with the interstellar medium, from just an interaction of the halo, which is the remnant of the ejection during the asymptotic giant branch, or to the complete merging of the planetary nebular shell with the interstellar medium. In this sense, the aim of this paper is the investigation of the real shape of the diffuse halo of NGC 651, studying its kinematics, composition, and interstellar interaction. In this sense, the authors analyze both optical observation and infrared data. Regarding optical observation, they acquired different high-resolution narrow-band images using two different cameras, Camelot and Alfosk, and also high-resolution broadband composite images using Osiris at Grand Tecan. This is an image obtained from the combination of the Grand Tecan and NOT images. You can see the wealth of features that are present in this nebula. Starting from the center of the main nebula, there is the ring. In the inner part of the ring, there is the presence of emission of hydrogen alpha and oxygen free, while the ring is delineated by the presence of emission of nitrogen 2 at the tips of the ring and hydrogen alpha. The central region of the lobes, in the central region of the lobes, there is the presence of emission of oxygen free, and the lobes are delineating by the presence of emission of nitrogen 2. There are also present some dark patches, which are indicating the presence of foreground absorbing material. Then you can see that the lobes are extension tips, in which there are present in the southeast regions a bow shock feature, and in the opposite part there are at least 3 bow shock features. In this image, you can see the first-time detection of this envelope. In the eastern part of the side of the nebula, there is this arc-like feature, in which there is emission of, principal emission of hydrogen alpha and oxygen free. And so there is the white arrow is the direction of the motion of the central star. And you can also see in X, Y, Z the position of free blobs in which there is the emission of nitrogen-2. They also performed a long-slit high and low dispersion spectroscopy in order to study to map the kinematics of these nebula. You can see that they try to map uniformly all the different regions in the nebula. And here you can see an example of position velocity map. Where there is at the right there is a synthetic model, and at the left is what they have obtained from the first long-slit spectroscopy. So they found that the velocity of the halo show small differences between the different parts of the halo, but also with the systemic velocity of the nebula. And so the velocity of the halo is blue shift, and so the halo is approaching us, and which means that the position of the halo is between us and the main nebula. They also exploit infrared archival data in order to see if they find the same things that they find in the optical analysis. And from these two images, you can see that they found that there is the presence of the envelope in the nebula, and there is also the presence of the arc-like features. So, conclusions, they confirmed the presence of the well-known bipolar main nebula, but they also found for the first time the presence of an arc-like features. And they concluded that this halo is the halo ejecting during the AGB phase, which is interacting with the interstellar medium. And the arc-like features, it's given by the motion of the nebula, which compressing the halo, forming this feature. And the free blobs that they see is the material that are being stripped from the halo during the interaction with the interstellar medium, and which are in emission of nitrogen-2. And that's all.
Any questions? One question.
If you can go back to the slide with the table, the one with the telescopes and the filters. Yeah, this one. Why did they use the small telescope with a narrow band filter and the huge one with a large wide band?
Broadband.
Yeah, because the ESA-80
Yes.
and the NOT are small telescope.
Yes.
The first one is 80 centimeters, the second one is 2.4 meters, and the Grand Decan is 10 meters. So I was expecting to use a wide band filter with a small telescope because you get not enough flux from the small telescope, and the narrow band filter from the huge one because they're serving a small spectral range. So did they explain why they
No.
do the motivation?
No.
Maybe my idea is small.
Okay, other questions?
Yeah, the filters generally use Johnson, Bessel filters, or Sloan
Yeah.
filters. Why you write the H alpha or this forbidden line?
Sorry, I didn't understand the question.
Filters should be slow, UGRIZ, like that.
Okay.
Or Johnson filters.
Sloan and another type of filter, I don't know.
Alpha is actually alpha is emission line, not the filters.
The OS6 order sorter filter. Don't know. What is the type of filter?
Another page on the spectrum. I remember you write long slit, high dispersion spectrum. I mean high dispersion or high resolution. Next page. Next. Here. Yeah. The first line. Long slit, high dispersion spectroscopy.
High dispersion
or
and low.
high resolution.
Can I say high dispersion or high resolution?
No, high dispersion. The high dispersion. Dispersion. Okay.
So, okay, we have some time, so that's it for it. Let's thank you very